Welcome to the Deep Dive. This is where we take a whole stack of sources, research papers, articles, and really try to boil them down for you. We find the most important bits, the surprising stuff, and sometimes, the really mind-bending nuggets of knowledge.
Exactly.
And today, we're plunging into a huge global challenge, water scarcity. It's something we hear about a lot, and there's this constant search, this quest for energy-efficient ways to purify water.
Right. We need to move beyond those, traditional methods that just consume enormous amounts of energy.
Definitely.
And that's why techniques like interfacial solar evaporation have really started grabbing people's attention in the scientific community.
Interfacial solar evaporation.
Yeah.
Okay, break that down a bit.
Yeah, so the basic idea is actually quite elegant, quite simple. You focus the heat right there at the liquid-vapor interface.
The surface where water actually turns into steam.
Precisely, yeah. And by doing that, you minimize the heat that gets lost down into the bulk water underneath. It's much more efficient, and it can seriously boost the purification performance.
So it's about being smarter with the heat you're using.
It's exactly that.
Yeah.
Really smart with the energy input.
Okay, but here's where it gets a bit weird, right?
Mm-hmm.
There's this mystery. Researchers started seeing something they called superthermal evaporation, which means water evaporating way faster, like surprisingly faster than our standard thermal physics calculations would predict.
It really looked like the water was, bending the rules somehow.
Especially when hydrogels were part of the setup. It seemed almost like magic, but, there has to be a scientific reason.
Oh, absolutely. And that's really our mission today, isn't it? To kind of unpack this puzzle, we're going to dive into some really groundbreaking new research here.
Research that gets down to the molecular level.
Yeah, exactly. Giving us an understanding of how this enhanced evaporation actually works. And this deep dive, well, it's going to reveal some pretty surprising things that challenge assumptions we've held for a while.
And you mentioned simulations, like computer models.
That's right. Cutting-edge molecular dynamic simulations. You can think of them as these incredibly powerful virtual microscopes.
Oh, wow.
They let us literally watch individual water molecules moving, bouncing off each other, interacting in real time. It gives us insights that, honestly, you just couldn't get from a physical experiment alone.
Okay, so let's get into it. What was the thinking before these simulations? You said there was this super thermal effect. How are people trying to explain it?
Well, for quite a while, the scientific community was sort of split. There were two main ideas, two competing hypotheses, really, trying to make sense of it.
Like two different detective theories trying to solve the case.
Kinda, yeah. So hypothesis one of the main contenders, was often called the reduced latent heat theory.
Reduced latent heat. Okay,
Yeah.
latent heat is the energy needed to turn liquid into gas, right?
Right.
Without the temperature changing.
Exactly, that specific chunk of energy. So the premise here was that maybe the hydrogels were somehow making the water itself easier to evaporate, reducing that energy requirement. The theory suggested that when water gets confined in the teeny tiny pores inside a hydrogel, it might form different states. They specifically talked about intermediate water. As opposed to free water just floating around, or bound water that's really tightly stuck to the hydrogel material itself.
Okay.
And the idea was this intermediate water was, let's say, less strongly bonded together, so it required less energy to break those bonds and turn into vapor.
This sounds pretty intuitive, actually. Like the hydrogel is kind of pre-softening the water for evaporation.
It does sound plausible, doesn't it? But this is where those new simulations come in, the ones done in a dark environment, meaning only thermal energy, no light involved yet.
Right. So how did they test this softened water idea without light? What did the data show?
Well, that's the power of the simulations. You can control the conditions precisely. And the key finding, the really crucial reveal, was this. For a specific amount of heat put in right at the interface, the evaporation rate was basically the same. It stayed consistent whether you had a hydrogel there or just pure water.
Oh, so the hydrogel didn't actually speed things up just by being there in the dark.
Not in terms of making the water inherently easier to evaporate, no. It directly challenged that idea that just forming these different water states was the key to enhanced evaporation.
Did they look at the energy differences between those water states?
They did, and the analysis was quite detailed. They found the interaction energy of that intermediate water was only about 12% different from free water.
12%? That doesn't sound like much.
It really isn't. It's nowhere near significant enough to explain the huge jumps in evaporation people were seeing in experiments. It's like blaming a tiny nudge for causing a massive avalanche.
Okay.
And interestingly, they found the bound water, the stuff really stuck to the hydrogel, was actually the most difficult to evaporate, which makes sense.
So the whole reduced latent heat idea, based on these simulations, seems unlikely to be the main driver.
Pretty much, yeah. It suggests it's not about the water itself becoming fundamentally easier to vaporize.
And you mentioned this lines up with other recent work.
It does. Several other recent studies have pointed towards the idea that when you see enhanced evaporation in these porous materials, it's often because they're better at absorbing energy from the surroundings, maybe extra heat, or, as we'll see, light, rather than the water's properties fundamentally changing.
So it flips the focus from the water itself to the energy input.
Exactly. Which brings us very neatly to the second hypothesis.
Hypothesis 2, what was that one?
This one was called the photomolecular effect. A very different idea and, frankly, pretty revolutionary when it was proposed.
Photomolecular.
Hmm?
Photo means light, right?
Yes. So this theory suggested that the incoming photons, the particles of light itself, could directly physically knock off or cleave water clusters from the liquid surface.
Knock them off, like directly using the light energy.
Kind of like that, yeah. It's often described as being analogous to the photoelectric effect, where light hits a metal and knocks electrons out.
Right, okay, so light hitting water and knocking water clusters out.
That's the core idea. And this is where the hydrogels become potentially really important again, but for a different reason.
Ah, because of all those internal surfaces.
Exactly. Hydrogels, with all their complex internal nano and micropores, create a massive amount of liquid vapor interface area.
Like a sponge, giving the light way more places to hit the water right at that boundary.
Precisely. More targets for this potential photomolecular effect to happen.
Okay, so how did the simulations investigate this idea? You can't really simulate every single photon hitting the water, can you?
No, that would be computationally immense. But here's where they got really clever. They used the fact that light, like sunlight, isn't just particles. It's also an electromagnetic wave.
Okay, with oscillating electric and magnetic fields.
Right. So instead of simulating photons, they used carefully controlled alternating electric fields in the simulations.
To mimic the effect of the light wave shaking the water molecules.
Exactly, to isolate that electromagnetic interaction, that sort of shaking effect of light, separate from just pure heat.
That's smart. And what happened? When they turned on this alternating electric field in the simulation, what did they see?
Well, this is where it got really dramatic. Applying that alternating electric field caused a huge increase in the evaporation rate.
For both pure water and water in the hydrogel.
For both, yes. But, and this is the kicker, the enhancement was much more significant when the water was inside the hydrogel.
Really? How much more?
Okay, get this. Compared to just thermal evaporation, the rate with the electric field alone was about 1.44 times greater for pure water. But for the hydrogel confined water, it was about 2.38 times greater.
Wow, that's a big difference. So the hydrogel really amplifies the effect of the electric field.
It seems to, yeah. It's not just a small boost, it's a substantial leap, especially in the hydrogel case.
And what about the energy? If the electric field is adding energy, does that mean less heat is needed?
That's exactly what they found. As they increased the strength of that alternating electric field, the amount of thermal energy, the heat they needed to input to keep the evaporation going, actually decreased.
So the electric field is actively doing work, contributing energy to the evaporation process.
Yes, it's taking over some of the energy load from the thermal source. They even found something they called a cutoff electric field strength, or E-cut.
Cutoff, meaning?
Meaning, at that specific field strength, the evaporation was driven entirely by the electric field. No extra heat input was needed at all.
Incredible. And was that cutoff point different for the hydrogel?
It was. Crucially, the E-cut was lower for the hydrogel system.
Ah, reinforcing the idea that the electric field has a bigger impact when water is in the hydrogel.
Exactly. It's like the hydrogel structure makes the water more susceptible, more responsive to that electromagnetic stimulation.
And it wasn't just the strength of the field, right? You mentioned frequency.
Frequency was also critical. They observed that as they increased the frequency of that alternating field, the rate of evaporation went up significantly.
Higher frequency, more evaporation.
Yep. And conversely, if they used a DC field that's a direct current, zero frequency, there was no enhancement observed at all.
So it's definitely about the alternating, the oscillation, the shaking.
It really seems to be, which has practical implications, right?
Yeah.
It suggests that maybe using higher frequencies could allow for enhanced evaporation, even with lower, perhaps more achievable electric field strengths. That could be a big deal for efficiency in real-world systems.
Okay, this is fascinating. So the simulations strongly point towards this photomolecular effect, driven by the electric field component of light, especially amplified by hydrogels. But what's happening at the molecular level? Why does the hydrogel help so much? What's the actual mechanism?
Right, let's zoom back into that microscopic view the simulations provide. It reveals this really intricate, almost like a dance, involving water
Water
clusters.
clusters, like little groups of water molecules sticking together.
Exactly. What the simulations showed is that the interaction between the hydrogel material itself and the water molecules actually perturbs or disturbs the normal hydrogen bond network between the water molecules.
It messes with how they normally connect.
Yeah, it sort of nudges them around, and this disturbance actually makes it easier for larger clusters of water molecules to form.
So the hydrogel encourages clumping.
In a way, yes. Specifically, it leads to a greater number and also larger sizes of these water clusters forming right there in the liquid-vapor interface region.
That crucial zone where evaporation happens. So the hydrogel isn't just a passive container. It's actively promoting these clusters at the surface.
It seems to be playing an active role, yes. And then the alternating electric field comes into play.
The shaker.
The molecular shaker, exactly. It induces vibrations, it makes the molecules in these clusters translate, move around, and rotate more vigorously. All this motion makes them more susceptible to breaking apart, to cleavage, and ultimately to evaporating.
But you mentioned something earlier about an indirect pathway. Do the big clusters fly off whole?
Ah, that's a key detail. What the simulations revealed is that the really large clusters think bigger than just 2 or 3 molecules stuck together, what scientists might call trimers or larger aggregates. They generally don't just evaporate directly as a big chunk.
Okay, so what happens to them?
Instead, the electric field helps them to break down. It fragments them into smaller clusters, maybe dimers or trimers, or even individual single water molecules.
And those smaller bits are what actually evaporate.
Exactly. It's the smaller fragments that successfully make the leap into the vapor phase. The electric field facilitates the breakup, creating the evaporable pieces.
Do they track these clusters in the simulation to confirm that?
They did. They followed the trajectories of these larger interfacial clusters, and the difference was striking. In the hydrogel case, with the electric field turned on, something like 16% of these big clusters broke apart into smaller pieces that then went on to evaporate and condense somewhere else in the simulation box.
16%.
And
Without the field.
without the field in the hydrogel, it was only around 7%. And interestingly, for pure water, even with the field, those large clusters almost always just fell back into the bulk liquid. They didn't really break apart effectively.
Wow, so that really highlights the synergy, doesn't it? The hydrogel helps form the big clusters.
And the electric field is much better at breaking apart those specific hydrogel-induced clusters for evaporation.
It's like the hydrogel sets them up, and the electric field knocks them down, but in pieces.
That's a pretty good analogy, yeah. The hydrogel gathers the crowd at the surface, and the electric field helps individuals leave that crowd by breaking it up first.
Okay, so let's pull this all together. After this whole deep dive, what's the main takeaway? What's the core insight here?
Well, I think the study provides really strong, quite compelling support for this photomolecular effect being the dominant mechanism, especially for the enhanced part of the evaporation.
So it's not about the water magically becoming weaker inside the hydrogel.
No, it doesn't seem to be about some pre-softened state or reduced latent heat, fundamentally. It appears to be much more about how electromagnetic radiation, like sunlight, which acts like an alternating electric field, how that field interacts vigorously with water clusters right at the interface, breaking them apart and significantly boosting the evaporation rate.
And that boost is particularly strong when hydrogels are there because they help create those initial clusters that the field can then act upon.
Precisely. It's a two-part mechanism almost. Cluster formation facilitated by the hydrogel, and then cluster cleavage driven by the electromagnetic field.
And understanding this fundamental science,
Yeah.
how does that help in the real world?
Well, having this deeper molecular level understanding gives us a much more solid foundation for designing better technologies. It can guide the development of more advanced solar evaporators, perhaps by tuning the hydrogel structure or even exploring how to best apply external fields. It helps optimize these energy-efficient water management systems we so desperately need.
Translating that tiny molecular dance into potentially solving huge global problems.
That's the goal, ultimately.
Okay, so for you, our listener, something to think about as we wrap up. Here's a bit of a provocative thought for you. We've just heard how precisely controlling an alternating electric field, mimicking light, can dramatically influence something as basic as water evaporation, especially with hydrogels.
Hmm.
So consider this. What other everyday processes, things we take for granted, might be significantly enhanced or optimized if we could harness these often unseen electromagnetic interactions at the molecular level?
It does make you wonder, doesn't it?
Yeah, it really raises a big question about how much more there is to discover about the hidden dynamics, the forces acting on matter all around us, shaping our world in ways we might just be starting to understand.
A lot left to explore, for sure.